Hello, my name is Leftaus. I'm a graduate student from the University of California, Los Angeles, and I'm here to present my work. Thank you very much for coming. My work is entitled Non-Uniform Window Decoding for Multidimensional Spatially Coupled LDPC Codes. This work was done with my former lab mate, Homer Esfahanizad, who is currently serving a postdoc at MIT, and my advisor, Professor Laura Dolachek. First, let's get a little background. We're all fairly familiar with LDPC codes and their many coding benefits, including fast decoding through belief propagation. LDPC codes are fully defined by their tanagraph and the connections between the variable nodes and check nodes. Spatially coupled LDPC codes are an important subclass of LDPC codes, which are constructed by concatenating multiple LDPC codes into a chain. Through this coupling, SC codes achieve capacity approaching performance and allow for low latency window decoding, as shown in the figure and the representative parity check matrix. As a reminder, window decoding works by performing belief propagation on the subgraph defined by the window, decoding a set of targeted variable nodes, and then moving the window one step along the chain. Note that we color code them as follows, where blue indicates targeted variable nodes and green indicates decoded variable nodes. Multidimensional spatially coupled LDPC codes are a further extension of SC codes where coupling is performed along multiple dimensions. In the literature, coupling along different dimensions may vary, but in this work, we consider two-dimensional coupling where multiple SC codes are laterally connected into one long chain. These codes have demonstrated outstanding finite and asymptotic performance, which makes them a viable candidate in coding for multidimensional non-volatile memories, such as 3D Flash. Some examples of these benefits are listed here, such as robustness to burst ratios and flexible finite length design. We add on to this list by demonstrating how to utilize the multidimensional coupling to create flexible low latency decoders. To our knowledge, the best known latency decoder for MDSC codes uses a natural extension of window decoding where each individual SC code maintains its own windows, all the windows decode synchronously, and then move one step in unison, as shown here. This can be seen as decoding one large window among the same parts within the SC codes. We consider this as the uniform window decoder because the shape of the window is evenly distributed among all the SC codes. While this offers the same latency and complexity benefits as regular window decoding, it does not take full advantage of the unique coupling provided. As such, we provide a solution to that, known as non-uniform window decoding. Non-uniform window decoding works by assigning a different window size to each constituent code based on which variable nodes are currently being targeted for decoding. This decoding works by utilizing the sparse coupling among the constituent codes to select the variable nodes that would maximize the decoding probability of the targeted variable nodes. To provide some intuition, let's consider some scenarios. The graph on the right represents an MDSC code construction where the blocks are individual LDPC codes, the rows are the individual SC codes, and the columns are the same segment within all the SC codes. Arrows indicate variable to check node connections. As such, 0, 0 is connected to 1, 0 by a variable to check node, but connected to 0, 4 by check node to variable node connections. Assume that we want to decode the section 1, 0. Consider the scenario where this section is directly connected to all the sections in the same segment. As such, all of them provide equal amounts of information because they can directly provide their information to the target variable nodes. And note that the closer a segment is to decoded variable nodes, the more beneficial information it provides. As such, a possible good window shape might be the one seen on the right. But when the code coupling is very sparse, the number of sections that this section is directly connected to is very few. And in fact, the distance between sections can be very large to these connections. As such, it is not clear whether something that's further away but closer to decoded variable nodes versus something that's closer but further from the decoded variable nodes isn't better or worse. As such, a possible good window shape might be the one seen on the right. Additionally, observe that all connections are not symmetric. There are variable to check node connections and check node to variable node connections. So the sections this one is connected to differs based on which connections is used. And it's not clear which connection provides the best information again. As such, a possibly good window might be this that prioritizes check node to variable node connections. We can see that there is a lot of nuance in this new construction that can be exploited to make better non-uniform shaped window decoders. As such, our key contributions are as follows. We provide a new, more general MDSC ensemble to allow for varying the coupling along different dimensions. We provide density evolution equations so we can analyze this ensemble. we present a new novel non-uniform shaped window decoder and provide its key design parameters, such as the order which the target variable should be decoded in, the shape of the windows, and the number of decoder iterations used per window. We additionally show how to optimize the design parameters using density evolution for the binary erasure channel and provide some insight into decoder design. So now we provide some simulations to show the efficacy of our construction. Some notation. DLDR are the degrees of the variable nodes and check nodes respectively. L2 is the number of constituent codes coupled together. Gamma 2 is the maximum coupling distance, which specifies how many codes can a single section be coupled to. T is the edge density, which specifies the percentage of edges used to connect the codes together versus connect within the code themselves. And C is known as the window decoder complexity, and it specifies the number of variable nodes used in the decoder. This is the analogous to the window size in the one-dimensional window decoder and acts as a measure for latency as well. Now we shall provide some simulation results to demonstrate. In this table, we present different MDSC code constructions and the best window shape to maximize the decoding threshold to achieve the specified decoding error of 10 to the -2. Note that all C were chosen such that a uniform window shape could be the optimal one, as shown here and here. We see that as the coupling gets sparser and sparser, as gamma 2 and T get smaller and smaller, the more non-uniform the window shape, the optimal window shape becomes, and can take full advantage of the sparse coupling to provide better performance with the same exact complexity. Now we demonstrate how our codes perform in the finite length regime. The following is the average bit error rate averaged over many realizations of the code in the ensemble. The code length is 9,000 and the design rate is 0.45. First, observe this circle. The blue curve and the red curve have the same window size complexity, where the blue curve is a uniform decoder and the red curve is our non-uniform decoder. We can clearly see the magnitude of improvement in the bit error rate, even though they have the same exact decoding performance. Secondly, we can compare the orange and the green curves, where the orange is for the uniform decoder and green is for the non-uniform decoder. These two decoders have very similar bit error rate performance, but the non-uniform decoder achieves it with a factor of 3 reduction in window size complexity. Thus, the finite simulation results also confirm the asymptotic results, that non-uniform decoders better utilize the code structure for improved error correcting capability. As such, we introduced a new non-uniform window decoder that allows for more flexibility in the trade-off between performance and decoder complexity, and demonstrate the significant improvement in both asymptotic and finite length performance of our new decoder. Ongoing work is about designing heterogeneous multidimensional SC codes for improved flexibility in code design, such as rate and degree distribution, and show their efficacy in being used for time-variant channels. And there's plenty of opportunity here to also utilize the code structures to improve decoder performance. This ends my presentation, and here are my references. Thank you very much for coming, and I hope you all enjoy the rest of your day.